Start a brief introduction to what is calculus is about. Again, unfortunately, this is not in the textbook, so you do have to listen. So what is calculus? Because it sounds so amazing, sound very cool, the whole course is about calculus, but what is it? Well, it's something useful. It's not something, it is quite useful. So the question is, how do we measure the gradient of each point? So what do they mean by gradient? How do I find the gradient here? Draw the tangent. How do I find the gradient here? I mean, obviously that's 0, but what's the gradient there? It keeps changing. So as you can see, the gradient at each point changes from point to point. So now to answer this question, we're going to, so these are puzzle mathematicians for hundreds of years until in the 1700s, they start to make some breakthrough. Okay, so there are two main branches of calculus. One is called differential calculus, which is what you're going to do in this topic. It involves calculating the gradient. And the other one is called integral calculus, which involves the process of integration, involves finding the area under the curve. For example, what's the area of that section? Again, all of these are very difficult for people in the 1700s or before that. So, but then after that, they come up with the machinery, the calculation, the calculus to do these things. That's why it's called calculus. You actually calculate stuff that's useful. As you can remember the quote, necessity is the mother of invention. Okay, what will be the applications of calculus? We'll be covering in year 12 in physics, particularly in motion of objects, calculate the speed of objects. In economics, find the maximum profit or minimize the cost. How to sketch complicated curves such as this. Find the volume of 3D shapes like this one. But if you read the history books, Archimedes, not just a famous physicist, he's also a very famous mathematician. He's the first person credited with finding the volume of sphere using the method of exhaustion. Okay, you can look up in Wikipedia if you are interested. So some people have discovered that quite early. However, unfortunately, his work was lost for for maybe 1,000 years before people would discover that book again. So some people actually have some idea of calculus very early on, which is quite amazing. But somehow the work got lost and got found inside I think I read a documentary like inside Bibles. People write stuff on it and say, oh, this guy discovered. Very smart. Okay. Why is it called calculus? The word calculus comes from the Latin word calculus, meaning counting impediments. Calculus has historically been called infinitesimal calculus. What is infinitesimal? Infinitely small, very small. We will see later on why this topic involves the very small. Again, that comes later on. And the next question is, when and who invented calculus? It's due to these two persons. Isaac Newton, which you all know, many people know. A lot of people know Newton, but a lot of people know that's his first name. Yeah, but anyway. Another less well known, he's actually a German judge. He's not a he's a judge, but he does maths as for fun. So he's not so both of these independently discover calculus. And because they independently discover calculus, they come up with different notation. He expressed much better. His notation still survives today. His notation used more on physics because he applied it to physics. But he's not very great expressing himself. But this guy's very great expressing himself. Very good. Both are very. This is German. This is English. So Cambridge, right? Okay. But anyway, you can read the history books. Newton was studying motion in physics and invented calculus to explain the motion of objects. He published his discovery of calculus in his famous book called the Principia in 1687. So what age is that? Who's good at maths? 24. Oh. No, not 24. 44. 44 is still pretty good. Yeah, but there's no Nobel Prize at that time. So, but he's yeah. But anyway, Leibniz, this guy called Leibniz, published his discovery of calculus some years before Newton. So people thought, so there's a saying, publish or perish. So if you don't publish it, someone may publish before you. Say, oh, I'm the first discovered, but someone else may discover before you. So make sure if you have some interesting idea, publish it. I mean, there's like other. Okay, now be careful is that this guy, the guy who invented the number plane, Descartes, invented the number plane, but he started to find the gradient of the tangent to the curve. If you read the history book, these two persons formalized it. He actually found the application. This guy also discovered calculus, but he was before Leibniz. He invented number plane. The first thing he does is let's start to find the gradient of the tangent. So it's quite interesting, but he's not as famous as these two guys. I think he's the most famous. If you go to China, like, oh, Newton, everyone knows. Like, most people know. Yeah, but anyway, because he found the application to physics, which is amazing. Anyway, let's move on. Let's move on. Now, this is the story behind it. In high school, we're still interested in how do I break. All right. Okay, so the question is, we still haven't answered the question. How do you find the gradient to a curve? Well, I have prepared this worksheet for you. Again, I got it somewhere. So it's already prepared for you. So we're going to find some rule. Maybe there's a rule that connects the point to the gradient of the tangent. Remember, gradient is rise over run. Pretty straightforward. So we're going to complete this table. So how does the table work? Instead of finding substitute x value, find the y value, I want to find the gradient at each of the x values. All right, let's start with something simple. Okay, obviously at 0, the gradient is 0. Easy. How about the gradient at 1? Let's count the grid. Now be careful. Yeah, is it the same scale? Yeah. So this is 1, right? Can you see this is 1? This is also, that's 0.5. Can you see that? You have to read the scale. Just be careful. So 1 over 0.5, what's 1 over 0.5? 2. So the gradient is actually 2. So the scale are a little bit different. So 1 over 0.5 is 2. Oh, no, that's 1. Sorry. 2. So how about the gradient at the other point? We can find the gradient by measuring the rise and the run. So it's already done for you instead of you have to use the ruler, because it's very hard to draw a 100% accurate curve. So it's done for you. Let's try this one. This is 0.5. This is, what's that? That's just, I think 0.5 as well. I think, yep. It's not to scale. I think the scale is shorter in the vertical axis. 0.5 over 0.5 is 1. Okay, let's do this first. Hopefully, we can discover a simple connection between the x value and the gradient, right? Hopefully. Let's try 2. Okay, let's count. This is, no, each bit is 0.5, 0.25, so that's 1. Agree? What would that be? That's from 6 to 3. What's that? Is that 3? That's 0.7. Yeah, 0.75. Thank you. Yeah, better maths than me. Yeah, that's 3, right? Yeah, that's good. Okay, use a calculator. What would that be? 4. Let's do some negative values. And we expect the gradient to be negative because it's going downward. So negative values, what would that be? That will be 0.5. That will be 1. Just do 0.5 again. That will be, remember it's negative. What would that be? That's 2. 2.5, is it? Oh, 1.5, 2.5. Okay, thanks for that. 2.5, that's 0.5. That actually makes my job easier. Okay, good. Because they're all 0.5. These are, oh, I just discovered they're all 0.5 except that one. That's 0.75. But anyway, what would that be? So you just double the y value. Right, pause. Continue. So you just double 1 over 0.5 is just 2. Remember, negative 2 because it's going down. That's negative 4. That's negative 5. Raise a hand. I'm sure you can see the pattern too. Raise a hand if you can tell me what's the connection between them. If I want to go x something to gradient, what do you have to do to the x value? Double it. Oh, that's pretty straightforward. Double. Oh, that's cool. So now we discovered the formula for gradient is equal to 2x. I mean, we worked out by experimentation. Is that the right formula? We have to prove it later on. We will be able to use algebra to prove this formula and the idea of limit, which we'll introduce later on. But for now, we'll just accept that by empirical data, that is true. that is going to be double the x value. Using this formula, we can now work out the gradient at this point. Remember, at this point, this gradient formula for the parabola, which is exclusively for x squared, not for anything, just for y equal to x squared, it double the x value. So no matter what the y value is, you don't have to look at it. Only look at the x value and double. So I'm going to ask a student, gradient of the tangent. Remember, it's the gradient of the tangent. So Ian, what's the gradient of at this point? 6. 2 times 3 is 6. Well done. Pretty convenient. And this one we can just double, which is already, oh, okay. MT, going to ask Aaron. -1, good, which is -1. Well done. Okay, pretty straightforward. Oh, we can go reverse. What if I give you the gradient? Does it give me the point? We can, isn't it? Because gradient equals to 2x. So if I know the gradient, 13, this is a bad position to write. So 13, so I just have to solve this very simple equation. So what would the x value be? Which is what? 7.5? Wrong. 6.5. How do I get the point? How do I get the point? Yep. Something, yeah, like that. And if you use a calculator, anyone? Say again. 42. 42.25. Yeah. I'll show you a non-calculator trick. Watch this. I learned that when I was young. My father told me this. He's not a math something, but he knows that's trick he learned from maybe somewhere. If these two numbers add up to 10, it doesn't have to be 5 as long as they add up to 10. 5 times 5, 25. 7 times 6, 42. Get it? Oh, works. But yeah, it's a party trick. You can use that as a party trick. Give me any. Just come up with any random two numbers like let's say again. 42 and 48. Bingo. 2, 8 is 16. 5 times 4, 20. Check it with your calculator. Want to bet? I could bet $100. Seriously, I'm gonna win. I'm gonna win for sure. But every time I bet, I never. Is it okay? Now I will just make sure. See, this is what we call magic. There's 2016. Oh my God, very smart. That's 2 years ago. No, 3 years ago. Anyway, all right. Okay, any question? All right. Okay, we got sidetracked. I'm so sorry. Let's move on. Okay, let's move on. Okay, now this is important again. So now we'll just calculate the gradient for the parabola. It's just 2x. But that's not useful because there's other curves like what if it's 5x squared? What if it's x squared plus 3x plus 4? There's so many different graphs. So do we just calculate the gradient by just measuring? That's just too slow. So we're going to introduce some new words. And in this topic, you'll be introduced to a lot of terminology, which I will use very often. So you have to know what they mean. So instead of saying the gradient function, we have a notation called the derivative, which has a symbol f dash x. F dash of x. Okay, f dash. So why it's called the derivative? Because it's derived from the original function. For example, the function we had was x squared. We found the derivative again by empirical data, not by proof. Right? That's a derivative. It got derived from there. And if you look at finance, they say financial derivative, not to do with this stuff, not to do with calculus, is derived, right? So if you go to study finance at uni, they have financial derivative, which means something else derived from it. Yeah. Okay. All right. So f dash of x is the gradient of the tangent to at this point. Is the gradient function. So for example, remember before I want to find the gradient at this point. I just have to substitute, right? It's a function that maps the x value to the gradient, right? It's a function that maps the x value. It's a map. Connect the x value to the gradient, right? It's a rule. So you just do 2 times 3, 6, right? Pretty convenient. And you can go backwards, given gradient, I could find the x values. So you go both ways. All right, cool. So sketch the graph below and then find f dash of x. So we can start with lines because lines is easy to find the gradient. For example, what if I want to find the gradient at 2? What's the gradient at 2? 2. 2 times 3 is 6. 6 times 3 is 9. 9 times 3 is 22. 22 times 3 is 36. 36 times 3 is 120. 120 times 3 is 180. 180 times 3 is 200. 200 times 3 is 400. 400 times 3 is 600. 600 times 3 is 800. 800 times 3 is 900. 900 times 3 is 1,000. 1,000 times 3 is 200. 200 times 3 is 400. 400 times 3 is 600. 600 times 3 is 800. 800 times 3 is 900. 900 times 3 is 1,000. 1,000 times 3 is 200. 200 times 3 is 400. 400 times 3 is 600. 600 times 3 is 800. 800 times 3 is 900. 900 times 3 is 1,000. 1,000 times 3 is 0. What's the gradient at negative 3? 0 again. So it tells me that the derivative must be 0 everywhere. For a straight line, the gradient is a constant, right? Which is easy. How about what if the gradient is not, what if the line is not a horizontal? What if it's like that? Let's try that. Let's find the gradient at 2, right? Well, draw this, right? 1 over 2. 2. What's the gradient at negative 1? Here. Also 2, right? Because it's this thing, right? You don't need to think like this one. You just go 0x plus 3, right? The gradient is 0. Well, that's for straight line. It's just easy, right? So if f of x equals to 2x minus 1, but the derivative is just the number in front of x. Pretty straightforward. What if f of x is 3, the derivative is 0? Okay, pretty straightforward. Pretty straightforward. Okay, so the next question is, well, these are straight line. We know them anyway, like just the gradient intercept form. Okay, that's good. But now we know how to express it using new language. Because now I'm now going to get you ready for the new one. Well, what if it's a parabola? Well, we know that already because at 2, it just double the x value, right? Because the derivative we learned from before that f dash of x is double the x value. Pretty easy. So this means that the gradient of the tangent at x equal to 2 is 4. So that means if I draw the tangent at 2, draw the tangent, that gradient is exactly 4. That's what that means. What would this mean? How do I find this one? F dash of 0. Alex Palmer. What's at f dash of 0? 0. Why? Because the gradient of the tangent is 0. Straightforward. Or you can use that formula. Both give you the same answer. And finally, Ethan, what's the gradient at negative 3? Negative 6. Yep. Right, can you make an effort to do means? Because you have to know what that means. It's like logarithm. What does log base 2, 4 equal to 8 equal to 3 mean? It means 2 to the power 3 equal to 8. So you need to know so every time you learn a new language, it's like when you learn a new word in English, write it in a full sentence. So when you learn a new concept, write it in a sentence too. So you say, means that gradient, means the gradient, you should do this, of the tangent at x equal to 0 is 0. Write it down. Then you can remember. How about the next one? Means the gradient, again, how do you learn a new word in English? Writing in a sentence. You should just memorize the definition. Oh, what does it mean? You should write it in a sentence you remember. Remember? You see, you remember, you do, you understand, do it. Tangent at x equal to negative 3 is negative 6. That's all that is. So if I measure the gradient at negative 3, like that, yeah, it gets very steep. It gets negative 6. Get the idea? All right, so it's still not very exciting. It's just a new language, just a new notation. All right, well, today, unfortunately, we can only, how long have I been speaking? We may even go through the next one if you want, but if you're not, we can just stay as one exercise. Okay, so now, so far, we've got this. That will get us started. It's a small step for me and then giant step. So now we made some giant steps that we got some this. And hopefully we can get some formula soon. Hopefully. But now we have to be satisfied with these two and just getting used to the notation. All right, so that means for any linear graph, the derivative is 3. That's all you have to do. Remember, stick to the notation. I want you to know the notation. Don't just go, just write 3. Write the notation because we'll be writing this f dash so many times. You remember that for the rest of your life because you have to do that. It's a language. Math is a language. Even though people say, oh, is that science? Yeah, it's a science. Is that art? It's also art. It's everything. It's everything. So now how about this one? Be careful writing in gradient intercept form. So therefore the gradient f dash of x, remember, it's negative 2 over 3. Write f dash of x. Joseph, what's the f dash of x with that guy? Yeah, what's the answer? 0. Yes, look, constant is 0. Thank you. Thank you. Be very careful. However, even though we don't have a formula for x squared, x cubed, we can find the gradient of a semicircle, even though it looks very complicated. But in fact, it's actually quite easy. We can do it geometrically. You just have to recall some of the properties of the circle is that the radius is perpendicular to the tangent. And we can capitalize that, take advantage of it. How do I do that? Very easy. What's the radius of this circle? Forgot. Oh, revise. What's the radius? Anyone? 5. How do I do that? Square root of 25 is 5. Yes. Okay, cool. Find the formula for the derivative. So if f of x is this thing, what's f dash of x? That looks so complicated, but you will see it's actually quite easy. Watch this. We start off with a xy, right? A general point, because gradient, derivative, the gradient function, calculates the gradient at any point. So we have to start with a general point. So we connect the origin to this point, right? Which is the radius. Let's find the gradient. The gradient is rise over run. Pretty easy. So the gradient of that radius is y over x. Pretty straightforward. How about the tangent? What is perpendicular to it? So therefore, m tangent equals to negative x over y, right? Perpendicular, right? Remember perpendicular, m1 times m2 is negative 1, yes. That's I got that. Reciprocal, negative reciprocal. That's in terms of y, it's not very good. I want f dash of x in terms of x only. Oh, well, what? It's just the answer staring at you. That's why, right? That's why. That's why. Okay, get the idea? So you go, oh, that's the formula. And we'll learn how to prove it after 5 exercise. Or I don't know. But now, just be satisfied, we can only find the gradient of the semicircle and the linear function so far. Because these are objects that's like easy, right? Circle and lines. Parabola is a different thing. It's a different curve. Whereas this this geometrical property can be found more easily. So we found it. Any question? And the question in the textbook, they will have question on this. So you just have to do that. Draw a diagram, something. Get the idea? But you won't be doing that in the future. In the future, you learn the formula. But for now, just remember the formula on the top and this one, and practice with it. Practice with the language. And then next lesson, or maybe we can wait 20 minutes. I'll show you the other half if you want to. But now, let's do the practice on the language. Now, before I could stop this presentation, please have a look at again some words again. But please read the fine print. Chord, secant, tangent. Let's draw something. So some new terminology has been used in this section. The words chord, secant, tangent were probably introduced in early years only for circles, but now are being used in the context of graphs or curves, and they mean the same thing, I think. Chord means the chord, such as bowstring, is the interval joining two distinct points P and Q on the graph. So for example, that's P, that's Q, that's the chord. How about secant? Secant is a line, not an interval, through two distinct points, like that. That's a secant. People say, oh, they're different things. That's a chord, that's a secant. They actually are a little bit different. And informally, a tangent, meaning touching a point T on a graph, is the line that continues in the direction of the curve is going at the point T. Think of the ray of light from the headlights of a car going around a bend. The definition used with circles means the curve only at T doesn't work for graphs. Because if the curve twists around, blah, blah, okay. Okay, good. So you will learn about tangent. So basically, a secant cuts the circle in 2 points. That's a secant. But tangent, it touches at 1 point, right? Touch at 1 point. But be careful of the definition of touch at 1 point. it still works for the parabola where I draw the tangent, it touches, right? There's a tangent. But it doesn't necessarily apply to all graphs, because if I draw a cubic that touches, but it ends up crossing. So be careful about touch at one point. It's not really touch at one point. It's really mean it's the line that continues in the direction of the curve. It is going at point T. That's what that means. It does touch at that point, but it may intersect the curve again at somewhere else. It may or may not. Be very careful. I mean, if I draw a tangent here, that's no problem. So the definition of tangent is now has to be more broader to include these cases. So again, the best way to learn something is by doing. So I need to stop talking. Can you please go to relevant exercise 9A, 9A, and start doing them. Thank you.